A mule team hauling ore from a mountain mine to a valley mill cost 20 cents per ton. A wire rope hanging in the air cost 9 cents. That 11-cent difference made millionaires and built entire mining districts where wagons couldn't go. By 1902, aerial tramways were moving more ore tonnage than all the mule teams in Colorado combined, running day and night on cables no thicker than a man's wrist suspended hundreds of feet above canyon floors. The conventional story of Western mining focuses on prospectors and ore strikes. The real story is about gravity pipelines that turned worthless claims into producing mines. It's May 3rd, 1891. Globe, Arizona. Temperature approaching 92 degrees by 10 in the morning. At the Old Dominion copper mine, 11 metal buckets hang motionless on a wire rope stretching 1,224 feet down a 100-foot drop from mine entrance to smelter. Each bucket holds 800 pounds. The Arizona Silver Belt newspaper has been running updates for weeks as construction proceeds on this aerial tramway built by the Trenton Iron Company of New Jersey. Mine Superintendent James Colquhoun stands at the upper terminal watching the first loaded bucket released onto the cable. Gravity pulls it down slope. As it descends, its weight lifts an empty bucket back uphill on the return loop. No steam engine required for the descent. No mules struggling on steep grades. No wagons running over animals on the downhill. The buckets move at walking speed, 3 miles per hour, steady and unceasing. Before this tramway, mule-drawn ore wagons cost the company 20 cents per ton to haul that same quarter-mile distance. The new system, 9 cents per ton, including all labor and repairs. The difference between profit and bankruptcy for a mine producing 500 tons monthly came down to $55 saved every 30 days. Multiply that across a year, across multiple mines, across entire mining districts, and you understand why these wire ropes changed the economics of Western mining more than any gold rush. The technology came from Europe. German wire rope manufacture in the 1830s replaced hemp rope on ships. Wire rope proved lighter, stronger, and could span distances hemp never could. Andrew Smith Halliday, working in California goldfields in the 1860s, realized that the same wire rope principles could move ore across canyons. His first system in 1867 used a single continuous loop of cable with buckets clipped directly to it. Halliday called it a ropeway. Mining engineers called it salvation for high-altitude claims. Charles Hodgson built the first system in the American West for mines at Treasure Hill, Nevada, in 1870 to 1871. That pioneer installation moved ore in grooved pulleys along a single wire rope in a continuous loop. The design limitation became clear immediately. Maximum distance 4 miles. Maximum load per bucket under 200 pounds. Speed frustratingly slow. But even this primitive system beat mule teams on mountain terrain where roads cost more to build than the mine was worth. By 1880, single-rope tramways dotted mining camps from Nevada to Colorado, moving small loads across short distances. Then German engineers Theodor Otto and Adolf Bleichert perfected the double rope system in 1874. 2 fixed cables provided the track for wheeled carriers to roll on. A third lighter cable ran in continuous motion, gripping the carriers and pulling them along the fixed cables. This Bleichert system proved revolutionary. Load capacity jumped to 2,000 pounds per bucket, distances extended beyond imagination, and reliability increased dramatically. The economics drove everything. In 1890, wagon freight from the mines at Bisbee, Arizona, to the railroad at Fairbank cost $6 per ton. The same tonnage by rail cost $1, but many mines sat where railroads couldn't reach and wagons barely functioned. A mine perched at 10,000 feet elevation with a stamp mill in the valley, 3,000 feet below, faced terrain where road construction cost exceeded the mine's total value. That's where tramways carved out their niche. the Highland Boy Gold Mining Company in Bingham Canyon, Utah demonstrated the calculation perfectly in 1897. Their copper-rich ore sat in car fork at elevation where wagon roads proved nearly impossible. Engineers surveyed the terrain and concluded a railroad would cost approximately 4 times what a tramway would cost. The company contracted with Trenton Iron Company for a Bleichert system, 2 1/4 miles on tangent throughout, no curves, straight shot from mine to railroad. Construction cost approximately $35,000 complete with all equipment. A railroad covering that distance with necessary grades and bridging would have cost $140,000 or more. The tramway moved ore for 9 cents per ton, including all labor and repairs. More importantly, it moved ore that couldn't move any other way at any price. That's the hidden mathematics of Western mining. The tramway didn't just reduce costs, it unlocked entire ore bodies that economics had previously rendered worthless. The Bleichert patent arrived in America in 1888 when Trenton Iron Company became the North American licensed manufacturer. Mining companies quickly recognized what this technology meant. The buckets varied between 7 and 9 cubic feet capacity depending on ore weight, typically carrying 700 to 1,000 pounds each. Heavier ores used smaller buckets to stay within cable weight limits. The system operated elegantly. Buckets hung from wheels rolling on stationary track cables. At each terminal, the buckets automatically detached from the haulage rope. Workers manually moved them around a circular I-beam system identical to what ski resorts would later adopt. The buckets got loaded or dumped, then reattached to the haulage rope for the return journey. Speed stayed slow enough that a man could walk alongside and manually guide buckets if needed. The Highland Boy Tramway by 1900 moved 275 tons daily with 115 buckets in continuous operation. Do the arithmetic. That's over 100,000 pounds moving through mountain air every 10 hours, replacing what would have required dozens of mule teams and teamsters and maintaining roads through avalanche zones and winter snowpack that could reach 20 feet deep. Aspen, Colorado, went on what one newspaper called a tramway building frenzy starting in 1888. Before tramways, ore descended Aspen Mountain in burlap sacks carried by mules. When mines reached lower-grade ore that needed higher volume to stay profitable, the math turned brutal. Teamster rates ran $2 to $5 per ton depending on season. Winter rates spiked because roads became impassable. Tramways cut that to 7 to 25 cents per ton and ran regardless of weather. The Aspen mine built a 3,000-foot system moving 10 tons per hour. The Compromise mine erected a Bleichert double-cable system where gravity pulled loaded buckets downhill while simultaneously lifting empty buckets uphill. A 25-horsepower electric motor assisted startup and handled uphill loads when no ore descended. The grandest installation, the Aspen Public Tramway, financed primarily by Jerome Wheeler, stretched nearly 10,000 feet through Spa Gulch from Tourtellotte Park to town. 59 towers, some rising 80 feet above ground, supported cables that ran day and night. Buckets spaced 100 feet apart, each with 600-pound capacity. The system didn't just move ore, it moved the entire economy of Aspen mining into profitability. Ore that couldn't justify wagon transport suddenly paid out. Lower-grade deposits became mineable. The tramway transformed the economics by collapsing transportation costs below the threshold where mining ceased being profitable. Remember those numbers from the Old Dominion, 9 cents per ton versus 20 cents. That 1891 installation proved you didn't need a long tramway to revolutionize a mine. 1,200 to 24 feet, 11 buckets, 800-pound capacity each. But look at what that eliminated. Mule teams struggling up and down a steep grade, wagons that required constant maintenance, Teamsters whose rates ate mine profits, winter closures when roads became impossible, and the perpetual danger of heavy ore wagons running over the mules on downhill grades. The tramway ran gravity-powered for descent, operated year-round regardless of weather, required minimal labor, and lasted decades with proper maintenance. The mine operator wasn't paying for innovation. He was paying to delete costs that killed profitability. The scale grew rapidly. By 1902, the North American Copper Company completed what was then the world's longest aerial tramway, 16 miles connecting the Ferris-Haggerty mine to the smelter at Encampment, Wyoming. The specifications tell the story. 270 towers, 16 tension stations, 293,000 to 275 feet of cable weighing 439,696 pounds, 1,250,000 feet of timber, 200 men employed for 6 months of construction, total cost $300,000. The system divided into 4 sections of 4 miles each because cable weight limitations prevented a single 16-mile span. This wasn't just engineering ambition. Encampment had no railroad connection. The mine sat in mountain terrain where road construction proved prohibitively expensive. The tramway represented the only economically viable way to move copper ore from mine to smelter. The Salt Lake Mining Review noted it was the first aerial tramway connecting inland towns not located on a railroad line. The thing moved ore through mountain air where no other transportation method could function at any cost. When the Saratoga Sun predicted Encampment would become the Pittsburgh of the West, they were betting on that 16-mile wire rope to make it possible. The Bleichert system proliferated throughout western mining districts. In Bingham Canyon, Utah, 4 major Bleichert tramways operated by 1909. The Highland Boy system moved 200 tons per hour, but was recorded carrying as much as 45 tons in a single hour during peak operations. The Yampa mine system ran 2 1/4 miles from mine to smelter, gravity-powered with 23 towers and 4 tension stations, capacity 75 tons per hour. The United States Mining Company operated a 2.5-mile system carrying 50 tons per hour. The Utah Apex ran 1 mile at 10 tons per hour capacity. Every one of these systems moved ore across terrain where railroads couldn't be built economically and wagon roads barely functioned. In Arizona's Bradshaw Mountains, the DeSoto mine completed a 4,000-foot aerial tramway in April 1904, connecting mine to railroad station. Capacity, 300 tons per day. The system operated entirely by gravity since the railroad station sat at lower elevation than the mine. The Bluebell Mine built a 3.3-mile tramway to Bradshaw Mountain Railroad's Bluebell siding in 1905. Capacity, 500 tons daily. These weren't experimental novelties. These were industrial arteries moving hundreds of thousands of tons annually, running 24 hours daily, operating in weather that closed roads for months at a time. Here's what the newspaper accounts usually missed. Tramways were dangerous. Cables broke. Towers collapsed. Buckets fell. Workers rode the buckets illegally and died when mechanisms failed or they lost their grip. The encampment system suffered a catastrophic fire at the reduction works on March 28, 1906 that destroyed the concentrator, boiler rooms, and powerhouse, causing over $300,000 in damage. Another fire struck in May the same year. When tramways failed, mining operations shut down completely because no alternative transport existed. A slide destroyed several towers of a Utah tramway in March 1910, forcing mines to revert to teams and wagons. Poor road conditions from winter weather meant higher costs and sometimes complete shutdown until the tramway could be repaired. The vulnerability became part of the economic calculation. Tramways represented a single point of failure, but the cost savings during operation justified the risk. Mining companies kept emergency repair crews on standby and stockpiled replacement cable and equipment. The Bleichert tramways could move astonishing tonnage. the Spring Canyon Coal Company in Utah, installed a system in 1913 capable of handling 2,000 tons of coal in 8 hours. That's 250 tons per hour, 4,000 pounds per minute, sustained hour after hour. The system used mine cars as tramway buckets, a clever hybrid where 2 loaded mine cars attached together got hoisted onto the cable, transported from upper terminal to tipple at lower terminal, then returned empty for another cycle. This wasn't ore, but coal, heavier and bulkier. Yet the tramway moved it across terrain where conventional transport couldn't function economically. By 1929, a 3-mile aerial tramway moved rock asphalt from a quarry down Water Canyon to crushing mills near Sunnyside, Utah. Then trucks hauled the crushed material 2 miles to a railroad. The economics kept changing as road and truck technology improved, but throughout the peak mining era, from 1890 to 1920, tramways remained the dominant solution for mountain mining transport. Death Valley's Keen Wonder mine demonstrated the system's elegance in extreme conditions. Discovered by accident in 1903 by Jack Keene and Domingo Etcherin, the mine hit its stride from 1907 to 1912. Unlike most Death Valley claims that produced excitement but minimal gold, Keen Wonder generated $625,000 to $682,000 in gold during its boom years. The secret: a 1-mile aerial tramway with 13 towers dropping 1,500 vertical feet from mine to mill. The system moved 70 tons of gold ore daily during peak production. In Death Valley summer heat that could shut down conventional operations, the tramway ran continuously. The heat presented challenges. Equipment overheated and water supplies diminished, but the tramway kept functioning when mule teams would have collapsed from the temperature. The installation cost significantly, less than building a road capable of handling heavy ore wagons in that terrain. More importantly, the tramway enabled the mine to operate profitably where conventional transport economics would have rendered the claim worthless, regardless of gold content. Miners quickly recognized that if buckets could carry ore, they could carry men. Photographs from Utah and Colorado show workers casually riding tramway buckets up and down mountains, sometimes sitting 2 per bucket, occasionally standing. The practice terrified mine superintendents who issued explicit prohibitions, but miners viewed the tramway as a free, rapid ride that beat hiking. The transition from ore bucket to passenger chair would have required minimal engineering modification, which explains why ski resort tramways appeared relatively quickly after mining tramways proved the concept. The similarity wasn't coincidental. Ski lifts directly descended from mining tramway technology. The detachable grip system, the towers, the continuous cable motion, the loading and unloading procedures all came from Bleichert patents and tramway engineering developed to move ore across mountain terrain. When the first ski lifts appeared in America in the 1930s, engineers simply adapted proven mining technology to recreational use. The Bleichert system specifications reveal the engineering precision required. Track cables ranged from 7/8 inch to 1 1/2 inch diameter depending on load and span. The continuously moving haulage cable ran lighter than the stationary track cables. Towers needed to withstand not just the static weight of cables and loaded buckets, but also dynamic forces, from wind, moving loads, and occasional bucket jams that could stress the entire system. Tension stations maintained proper cable tautness, as temperature changes caused expansion and contraction. Every splice in the cable represented a potential failure point that crews inspected constantly. The cables themselves required sophisticated metallurgy. Wire strands twisted into rope that could bend around sheaves hundreds of times daily without breaking, withstand exposure to rain and snow and temperature extremes from below 0 to over 100 degrees Fahrenheit, and maintain structural integrity while carrying thousands of pounds in suspended loads. Trenton Iron Company and later competitors manufactured these cables to exacting specifications because cable failure meant catastrophic accidents, destroyed cargo, and mining shutdowns lasting weeks. The tramway business became competitive. By 1897, an article in the New York Times mentioned 50 Bleichert-Bickable tramways operating in the United States. Manufacturers included Otto, Leschen, Brecco Ropeways, Siretti and Tanfani, Riblet, and Bullivant, which became part of British Ropes in 1924. The Mine and Smelter Supply Company in Salt Lake City became a major supplier of Finlayson tramways, a competing system. Fraser and Chalmers of Chicago entered the market as another licensed manufacturer. The competition drove mechanical improvements, better grips, more reliable detachment systems, stronger cables, more efficient terminal designs. By 1903, mining engineer T.A. Rickard pronounced the single-rope Halidi system nearly obsolete. The double-rope Bleichert system had become the industry standard despite costing 30 to 50% more than single-rope systems. Because maintenance costs on the Bleichert ran nearly half those of single-rope systems and capacity reached levels single-rope could never achieve. The Halidi system limited capacity to 75 tons per 10-hour day. The Bleichert system regularly handled 300 to 500 tons daily on major installations. The decline began in the 1920s. Open-pit mining technology advanced, allowing mines to move ore with trucks and shovels rather than vertical shafts and tramways. Road construction techniques improved and costs decreased. Trucks became more powerful and reliable. Conveyor systems offered alternatives for shorter distances. The economics that had favored tramways began shifting. A tramway at the Morenci mine in Arizona, built in 1970 connecting a limestone quarry to the Phelps Dodge smelter, could haul 2,000 pounds per bucket, but operated only briefly before a better limestone deposit was discovered closer to the smelter. Phelps Dodge dynamited the tramway in 1997. That trajectory repeated across the West. Tramways that had operated for decades got dismantled as alternative transport methods became economically competitive. But from 1870 to 1920, that 50-year window, aerial tramways moved more ore tonnage in the American West than any history book acknowledges. The systems ran day and night, winter and summer, through blizzards and heat waves, carrying millions of tons across canyons and gorges and mountain faces where wagons couldn't travel and railroads couldn't be built. Here's what the myth misses. Western mining wasn't about prospectors penning streams or gunfighters protecting claims. It was about engineering solutions to transportation economics. A mine with rich ore but prohibitive transport costs went bankrupt. A mine with moderate ore and cheap transport made fortunes. The aerial tramway collapsed transport costs for mountain mining from multiple dollars per ton to a few cents per ton. That cost compression opened entire mining districts that geography had previously locked away. The cables hanging in the air, some stretching miles between mountain peaks and valley floors, represented economic arteries more vital than any stagecoach route or wagon road. When mining engineers calculated whether a claim could operate profitably, transport costs dominated the equation. The tramway rewrote that equation across the West. The systems that remain today stand as skeletal monuments, tower frames rusting in mountain weather, cables sagging or snapped, terminals collapsed. The Pioche aerial tramway in Nevada, built in 1891 and operated until the 1930s, remains the only complete system still standing in that state. Gravity-powered, running from mountainside through town to the Godby Mill, it moved ore for 4 decades without consuming fuel beyond the initial construction. Tourists photograph it now, without understanding the economics it represented. The Keen Wonder Mine Tramway in Death Valley preserves 13 towers with cables still intact, climbing over 1,000 vertical feet in less than a mile. The National Park Service stabilized structures so visitors can see the engineering, but the industrial purpose, moving 70 tons daily through desert heat where no other transport method functioned, that context gets lost in the scenic photography. At the Grand Encampment Museum in Wyoming, reconstructed tramway towers display the scale and complexity, but they're static exhibits. The operating reality, 270 towers stretching 16 miles through mountain terrain, moving copper ore around the clock, that visceral industrial presence can't be reconstructed. The final calculation returns to that first number, 9 cents per ton versus 20 cents. The Old Dominion tramway and globe paid for its entire construction cost and saved transportation expenses within 18 months of operation. Multiply that across hundreds of tramways installed throughout the West. Calculate the ore tonnage that moved profitably only because tramways existed. Add up the mining districts that functioned only because aerial cables solved the transportation problem. The conventional story of Western mining focuses on ore strikes and boomtowns. The real story is that most of those boomtowns only boomed because wire ropes hanging in thin air made the economics possible. The prospector finding ore mattered less than the engineer calculating whether a tramway could move that ore profitably to a stamp mill or smelter. By 1920, mining had moved enough tonnage on aerial tramways to build a cable stretching from San Francisco to New York and back twice. Most of those cables hung from towers in mountain terrain where conventional transport couldn't function. They moved ore that created the copper wiring for America's electrification, the gold and silver that backed currency and built fortunes, the coal that powered industry. And they did it for 9 cents per ton when the alternative cost 20 cents or couldn't happen at any price. The last major mining tramway built in America probably dates to the 1970s or 80s before modern mining methods made them obsolete. But from 1870 to 1920, that 50-year peak, no technology did more to unlock Western mountain mining than the aerial tramway. Not the steam shovel, not dynamite, not the stamp mill, not even the railroad. Because all those other technologies required ore to reach them. The tramway solved the problem of getting ore from mountain to valley when nothing else could. It was gravity, wire rope, and cost accounting, and it changed the geography of Western mining more than any gold rush.